Today's topic is unitary operators. First, we define a unitary operator. Let H be a Hilbert space. A bounded linear operator T on H is said to be a unitary operator if and only if T star T is equal to T star is equal to I, that is identity operator. So here we find that T commutes with its Hilbert adjoint operator. So we can say that from the definition it is clear that T is a normal operator and T star is equal to T star T is equal to identity operator. So we have remarks. First remark is a unitary operator is bijective. Second remark is unitary operators are precisely those operators whose Hilbert adjoint operators are the same as their inverses. And third remark is a unitary operator is normal, which is clear from the definition itself. First, we prove the first remark, that is a unitary operator is bijective. So let T be a bounded linear operator on Hilbert space H and T be unitary. For x and y in H, let Tx is equal to Ty, then T star of Tx is equal to T star of Ty, and since T star T is equal to identity operator, so we have Ix is equal to I of y, and this implies that Ix is equal to y. And so we have shown that if Tx is equal to Ty, then x is equal to y, thus T is 1, 1. Next, we have to show that T is onto. Let y belongs to H, as T star is a mapping from H to H. So T star y is an element of H. Let us denote that element by x. Then we can say that there exists an element x in H such that T of x is equal to T star y, that is equal to I of y, because T star is equal to identity operator, and that is equal to y. So we have shown that for any y in H, there exists an element x in H such that Tx is equal to y, whereby T is onto. Next, we have to show that unitary operators are precisely those bounded operators for which Hilbert adjoint operators are the same as their inverses. So let T be a bounded linear operator and T be unitary. And then from first remark, T is bijective, and so T inverse exists. As T star is equal to identity operator, so T inverse of T star is equal to T inverse into identity operator. And since we know that composition of functions is associative, so we can say that T inverse of T into T star is equal to T inverse. And since T inverse T is equal to identity operator, so I into T star is equal to T inverse, and this implies that T star is equal to T inverse. So we have shown that if T is a unitary operator, then its Hilbert adjoint operator is the same as its inverse. Next, conversely, if we take any bounded linear operator T on H such that T star is equal to T inverse, then we observe that T star is equal to T inverse is equal, this implies that T star is equal to identity operator. And T star T is equal to T inverse into T. This implies that T star into T is equal to identity operator. Thus, we have shown that T star T is equal to T star is equal to identity, showing that T is a unitary operator. Next, we have to show that any unitary operator is normal, which is clear from the definition itself. Now we discuss a problem. Give an example of a bounded linear operator which is normal but neither self-adjoint nor unitary. Here I am giving an example of such an operator. You can also find some other examples. Let T is equal to 2I times identity operator from Hilbert space H to Hilbert space H. And we can easily check that this operator T is bounded and linear operator. Why? Because we know that identity operator is a bounded linear operator. And here, if we multiply identity operator by any scalar, then again it will be a bounded linear operator. So T is a bounded linear operator. And we know that its Hilbert adjoint operator exists. So T star always exists, and here T star is equal to 2I into identity operator whole star, that is equal to complex conjugate of 2I into I star. And since we know that I is a self-adjoint operator, that is I star is equal to I, and complex conjugate of 2I is minus 2I, so we have T star is equal to minus 2I into identity operator. So here we find that T is not equal to T star, so T is not a self-adjoint operator. Now we want to show that this is not unitary, so we find T star. T star is equal to 2I times identity operator into minus 2I times identity operator, and that is equal to 4I. And if we find T star T, then that is also 4I. And so we find that T star is equal to T star T, and so we can say that T is a normal operator. But since T star is not equal to identity operator, and this is also not equal to T star T, so we can say that T is not a unitary operator. Now we have a theorem which states that let S and T be unitary operators on a Hilbert space H, then statement A is T is isometric, statement B is norm of T is equal to 1 provided H is not a null space, statement C is product of S and T is unitary, statement D is T inverse is unitary. Let us prove this theorem. And since we want to show that T is isometric, so we have to show that T preserves norms. We find that for each x in H, norm of Tx whole square is equal to, by definition, inner product of Tx and Tx. That is equal to, by definition of Hilbert adjoint operator, that is equal to inner product of x and T star Tx. And since T is unitary, so T star T is equal to identity operator, and so this expression is equal to inner product of x and Ix, that is equal to inner product of x and x, implies that norm of Tx whole square is equal to norm of x square. Thus, we have shown that norm of Tx is equal to norm of x for every x in H. Hence, T is isometric. Now, we prove statement B, that is norm of T is equal to 1 provided H is not the null space. So, by definition, norm of T is equal to supremum of norm of Tx, where x belongs to H and norm of x is equal to 1. And in statement A, we have proved that norm of Tx is equal to norm of x. And so this expression is equal to supremum of the set norm of x, where x belongs to H and norm of x is equal to 1. And since norm of x is equal to 1, so each term in the bracket is 1, and so supremum is also 1. So we have shown that norm of T is equal to 1. And here we note that if H is the null space, so then H does not contain any vector whose norm is equal to 1. So we have a norm of T is equal to 1 provided X is not the null space. Now we have to prove the next statement C, and we have to show that ST is unitary. So first we find st star into st, that is equal to t star s star. We know that st whole star is equal to t star s star into st, and here we know that s is unitary, so s star s is equal to identity operator, and so we find that that is equal to t star t, and since t is a unitary operator, so t star t is equal to identity. And next we find st into st whole star, that is equal to st into t star s star, and that can be written as si into s star because t is also unitary. So t star can be replaced by identity operator, and that is equal to s star, and since s is also unitary, so s star is equal to identity operator. So we have shown that st into st whole star is equal to st star into st, and that is equal to identity also, and so we can say that st is a unitary operator. Now we prove statement D, that is we have to show that T inverse is unitary. St is given as unitary operator, so by definition T star is equal to T star T is equal to identity, and we know that T is equal to T double star, that means T star of star, and so T can be replaced by T star of star. So we have T star of star into T star is equal to T star into T star of star is equal to identity. From this expression, it is clear that T star is unitary. Why? Because T star commutes with its Hilbert adjoint operator, and its product with its Hilbert adjoint operator is equal to identity operator. So we can say that T star is unitary. As T is unitary, and we know that if T is a unitary operator, then its Hilbert adjoint operator coincides with its inverse. So T inverse is equal to T star, and since T is unitary, so T inverse is also unitary. Now we have a theorem which states that let H be a complex Hilbert space and T be a bounded linear operator on H. Then the following statements are equivalent. Statement A is T star into T is equal to identity operator. Statement B is inner product of Tx and Ty is equal to inner product of x and y for every xy in H. And statement C is norm of Tx is equal to norm of x for every x in H. That is, T is an isometric. Let us prove this theorem. First, we show that A implies B. So let A hold. Then T star T is equal to identity operator. And we have to show that inner product of Tx and Ty is equal to inner product of x and y for every xy in H. So we find inner product of Tx and Ty. By definition of Hilbert adjoint operator, we know that this inner product is equal to inner product of T star into T of x and y. And since T star T is equal to identity operator I, so this is equal to inner product of I of x and y, and that is equal to inner product of x and y for every xy in H. And so we have shown that B holds. Now we shall show that statement B implies statement C. So let B hold, that is inner product of Tx and Ty is equal to inner product of x and y for every xy in H. If we take y is equal to x in this expression, because this expression holds for any xy in H, so we find that inner product of Tx and Tx is equal to inner product of x and x for every x in H. And this implies that norm of tx whole square is equal to norm of x whole square for every x in h. So we have shown that norm of tx is equal to norm of x for every x in h. So C holds. It remains to show that statement C implies statement A. So let C hold. That is, norm of Tx is equal to norm of x for every x in H. And this implies that norm of Tx whole square is equal to norm of x whole square for every x in H. And this implies that inner product of Tx and Tx is equal to inner product of x and x for every x in H. And this implies that inner product of T star T of x and x is equal to inner product of I of x and x for every x in H. Why? Here we know that by definition of Hilbert adjoint operator, inner product of Tx and Tx is equal to inner product of T star T of x and x. And x can be replaced by identity operator I of x, because I of x is the same as x. And so we have this expression, and this implies that inner product of T star Tx and x minus inner product of Ix and x is equal to 0 for every x in H. And since inner product is linear in first argument, so this can be written as inner product of T star T minus I of x and x is equal to 0 for every x in H. And since here H is a complex Hilbert space and this inner product is 0 for every x in H, so here we know that this operator must be equal to 0. That means T star T minus I is equal to 0, and this implies that T star T is equal to I. So we have shown that statement C implies statement A. Thank you.